So today I'm going to be talking about a paper that I wrote that came out about 6 months ago now, which is about how to choose a maximum drift rate when you're doing a SETI search, and how what we know about astrophysics can inform which drift rates we decide to choose. So I have not gotten a chance to meet you all yet because I have been moving across the country, but just a quick introduction. I am a fourth-year PhD student in astronomy and astrophysics at Penn State. As Steve mentioned, I'm working with Jason Wright. And this coming year, I am in a visiting graduate student position at Breakthrough Listen, so I will hopefully be on site whenever that becomes a thing we can do again. And my PhD topic is in SETI. So before I move on, I would just want to acknowledge my co-authors on this paper, Jason Wright, my advisor, Emilio Enriquez, who was part of the Breakthrough team and really mentored me through this work, and of course, you've met Andrew. So now to kind of get into the science part, can everyone hear me all right? Just thumbs up real quick to make sure. All right, awesome. I'm in South Carolina right now with some rural internet, and we'll see how this goes. So I'll start out with some background and motivation, especially defining what I mean by a drift rate. If that title is not clear to you yet, that's totally fine. Some different algorithms that we use when trying to find drifting signals in data. Then some representative astrophysical systems where transmitters could be and what drift rates would be induced by those systems. And finally, kind of summarizing all of that into some nice results. So, what are drift rates? Why are they relevant to what we do in SETI? And what prompted the need for me to do a project on this? Why was the previous SETI literature not sufficient? So drift rates are changes of Doppler shift. So if you think about, you might have seen this figure before from ESO showing how the radial velocity technique for finding exoplanets works. You have a star, there's an exoplanet that's orbiting that star, and as a reflex motion, as the exoplanet orbits, the host star is going to wobble back and forth. And that wobbling, when it goes away from the Earth, we see the signal that it's emitting being redshifted, and when it comes back towards the Earth, that signal's blue shifted. So if you make a plot of that action over time, you see kind of this curve on the right. Can people see my mouse? I always just want to check. All right. So this is the radial velocity looking at a star with an exoplanet system. This is actually a plot from what many people consider the first exoplanet discovery paper. And as the exoplanet orbits, you see this nice sine curve in the radial velocities over time as the planet goes towards and then away, or sorry, as the host star goes towards and then away from the Earth as a reflex motion from its planet. So what I'm looking at is the time derivative of that radial velocity signal. So how quickly is the signal drifting? So at this point in the sine curve, there's the maximum slope. So that's your maximum drift rate, the fastest change in the radial velocity. And you'll notice that that happens around 0. So if you want to think about this in the physical system again, that's when the planet is passing between you and the star. So when it's changing from going towards you to away from you. The minimum drift rate happens kind of at these peaks and troughs where your slope is the shallowest. So that would be when the planet is coming directly towards or away from you. So that's kind of thinking about it in this frame of planetary systems. But when we think about it in how this affects our radio observations, we'll see it appear in waterfall plots. So I don't know yet how many waterfall plots you've seen, so I'll kind of walk you through this one. So we'll just start with the bottom center panel here. So what you're seeing is time on the y-axis and frequency on the x-axis. And here it doesn't particularly matter, but we'll say our time goes 0 at the bottom and then increases upwards, so which is actually kind of opposite how Breakthrough usually does the plots, but it doesn't matter too much. And what you see is this red kind of, oops, oh no, we're going back, there we go. This reddish linear feature here that's starting at some frequency and then linearly changing in frequency over time. And that slope in the plot is the effect that we call drift rate. So if you just tried to find this signal in the data by saying like, okay, let's just squash this along the time axis, where is the bright spot? You're gonna have a problem because the bright spot isn't concentrated at one frequency, it's changing in frequencies. So it's getting smeared across frequency channels. So if you look in the top plot, the red line illustrates this. If you were just to integrate this whole like block at the bottom and squash it down in time, you don't get a great signal to noise because the signal gets smeared along many frequency channels that are otherwise just filled with noise. However, if you know what that slope is and you account for it, then you can recover this nice blue high signal to noise line here, where you even can see these tiny peaks that are these sort of associated sidebands to the main signal. So spoiler alert, this is an astrophysical signal that we observed through Breakthrough Listen. This is Voyager. So the central set of panels here is the main carrier wave of Voyager. And on the right and the left, you have the associated sidebands. And with the sidebands, the effect isn't quite so drastic because they're wider band to begin with, so the drifting doesn't affect it as much. But you can still see that if you don't properly account for that drift, and you just integrate down without paying attention to the slope, then this red line kind of loses structure. You don't get these nice kind of peaked formations that might carry information or tell you that this is some signal that you're interested in. So we really want to make sure that we're accounting for the slope so we can get the maximum signal to noise possible and we don't lose fidelity on any of the structure. So I took that figure from ESO and edited it a little bit to show how this works for transmitters. So if you have a transmitter and it's just sitting perfectly in space and it's not accelerating with respect to the Earth, you would see a nice vertical line in the waterfall plot and we wouldn't have to deal with this. Unfortunately, relative accelerations are everywhere in space, and no matter if you're sitting on a planet or orbiting a star or even just floating around orbiting the galactic center, there's going to be some relative acceleration between you and the Earth. And that relative acceleration is what's going to cause this drift rate. So that affects the shape of the waterfall plot signal, and it means that we have to account for sloped lines when we're doing our searches and not just vertical lines. And I kind of mentioned this already, but what we're really looking at is the time derivative of the frequency. So how quickly is the frequency changing? And you can relate that back to the change in the velocity or the relative acceleration. So that's what this kind of dotted frequency equation is sitting in the corner here. So I think, yeah, I'm gonna keep going, but I just wanted to stop and ask if there are any questions so far. You could just give me a thumbs up if it's going all right. All right, cool. In that case, I'll keep going. So people have thought about this before. This is not a novel concept. There was a report called the Cyclops Report that came out in 1971, which was a NASA report talking about Radio SETI. And in that report, these ideas of like, oh, the signal is going to be drifting, so we have to make sure we account for the slope, did appear, but only very kind of in a cursory way. So they have this one paragraph where they talk about it in the context of a transmitter sitting on a planet that's rotating, because that causes a relative acceleration. And the authors basically do this order of magnitude thing where they say, well, Jupiter has an 8-hour rotation period, so if there was a terrestrial planet with an 8-hour rotation period, the size of Earth, and we stuck a transmitter on the surface, what would that relative acceleration be? And what frequency change would that cause over time? So they do this and they get this value of nu dot over nu. They report it as 10 to the negative 9. They're actually missing units there. That should be 10 to the negative 9 hertz. But if you use this kind of like, okay, what if Earth was spinning such that it had an 8-hour day, then what would the drift rate be, the maximum drift rate? You get this idea that it should be about 1 hertz per second if you're observing at 1 gigahertz. So every second you observe, you watch your signal drift 1 hertz over. So that comes out to a hertz per second over gigahertz, which you can rearrange into just nanohertz. It's a weird unit, but it is kind of a convenient way to report things. So you'll see me use that nanohertz unit kind of throughout the talk. And what I wanted to know was, this thing was written in 1971. And in 1971, we didn't know of any exoplanets. So now that we know what exoplanet systems look like, can we do better than just assuming an 8-hour day and finding some drift rate we think we'll expect as the maximum? Could that be a bad upper limit? And could there be a lot of physically possible systems that are exceeding that limit that we would miss if we said, okay, we're only looking for things below 1 nanohertz? So that's kind of how this project started. So now I'm going to take a kind of brief diversion into algorithms. So ideally, the solution to this problem is just search all the drift rates, right? If you don't know what the maximum one that's physically allowed will be, then just search as many as possible and problem solved. It doesn't matter what the physical limits are. But this takes time, right? If you're trying to do this with an algorithm, it's going to be an additional computational cost. And if there's no physical reason that the signal would be up there, why would you waste time searching? So I'll talk about some of the algorithms that we use to search for signals like this and the kind of scalings that they have. So like I said, why do you want to pick a maximum at all? Why don't you just search as many as you can? We're definitely in the realm of big data here, both just in the Breakthrough Listen project in general, but also astronomy as a field is moving into this direction of too much data to ever go through by eye or manually. So we really need to rely on algorithms to make new discoveries and sort and characterize our data. So that leads to computational constraints on how much data we can go through and exactly how much time we want to spend doing each task. So this is something that I saw was being talked about a bit in the interns channel, which is really cool. I kind of went into a deep dive on Huff and radon transforms when I was writing this paper because they're really neat. This is a way to find linear features in an image. And it was proposed in 1962 in this paper by Huff. And since then has come up a couple times in the SETI literature. So people have recognized that this might be a way to find drifting narrowband features in waterfall plots. And the way it works, I don't think I'll go into this too much, but it takes your image and converts it into a slope-intercept parameter space, or SIPS, which is literally just a grid of different slopes and different intercepts of lines that could be going through your image. Then it checks each one and sees which of the possible lines that it's guessing contain the most power. And I love this illustration up here in the top corner, where you have an original image, then you do edge detection on it. So there are many edge detection algorithms in image processing. I don't claim to be an expert in this particular part of the problem. But once you've done that edge detection, you can run a Huff transform on that image, and it'll find any lines or line segments that are present in that input array that you've given it. it can find both infinite lines and finite lines, which is pretty cool. And this kind of combination of sine waves that looks very pretty, in my opinion, is what that slope-intercept parameter space looks like. And anywhere you see a bright spot in that image is the corresponding slope and intercept of a line that it's picked up as a bright feature. So you might also hear this method called a radon transform. They're technically slightly different. Radon transforms are an inverse of the Huff transform, but they work in the same parameter spaces and they work in very similar ways. I don't know how well the GIF will come across with Zoom, but I'm going to hope that it's working, where there's this line that's kind of rotating through each point in the original image, and every time it does, it sums along that line and fills in the corresponding pixel in the slope-intercept parameter space. So once it has iterated all the way through, then you'll start to see these bright pixels appearing in the right-hand image, which is in your slope-intercept parameter space. Then all you have to do is ask your code like, hey, where are the maxima in this array? And that tells you the parameters that you want for the line that exists in the original image. So this is a cool method. There are a lot of pros to using this. You don't need any a priori information about where the lines are. You only need to tell it what max slope and max intercept to search to. So that's good because we have no idea what slopes these lines might come in at, what the drift rates of our signals might be. Another nice thing about this is that you can parallelize it very easily because you can just split the image into smaller like boxes and say, okay, this processor take this one, this processor take this one, and you can speed it up very easily that way. It's pretty robust to noise or occlusion. It'll pick up line segments, even in noisy data, or if they're transient, which is also good for SETI because often we say we're looking for continuous signals, but if something turns on for a little bit and is very bright, we could still pick it up with this method, which is nice. And it also finds all maxima simultaneously. So if you have multiple lines in an image, say like a drifting comb of signals, it will still find and report all of those, which is really nice, not just the brightest one. Unfortunately, it needs you to input a max slope. So it needs you to have a maximum drift rate for the algorithm. And it also scales in order n squared log n. So this is specifically an image size. So as your image gets bigger, it gets a lot slower. One thing that I did not put on here, but I want to say is in drift rate, it scales order n. So if you want to search twice as many slopes, then it'll take twice as long, which is better than n squared log n. So one other algorithm, I'm only going to talk about two, so that was the first one. The second algorithm that we use is actually what's used by Breakthrough Listen in the Turbo SETI algorithm that you might have interacted with in the last week or so. And it uses a method called tree summation. Tree summation has been used for a while in astronomy. It is an algorithm that was borrowed from pulsar de-dispersion. So if you're looking for pulsars in data, the travel of the signal through the interstellar medium will spread the signal out into sort of a, not actually linear, more complicated than linear, I think kind of a parabolic shape. And in order to find those parabolas in data, then you need to be able to kind of search a lot of different curves with a lot of different input coefficients. So it's a slightly more complicated version of the same problem. So in our case, we're just doing lines. We don't need any extra coefficients. So tree summation will sum along all potential lines up to some given slope. You input the slope, and it'll search for all lines up to that slope. And most implementations of this algorithm now take advantage of redundant sums. You can do this with the Hough transform as well, which is how you get it from order n cubed to order n squared log n. You can kind of change an n to a log n if you are clever about how you're saving your arrays. So the way that this works in the tree summation algorithm is, say you're looking for a vertical line in this first column. This is my kind of cartoon waterfall plot here. For a vertical line, you have to sum the first 3 pixels in this column with the next 3 pixels in this column. But if you wanted to search for the next kind of smallest slope, you would want to search the top 3 and then the bottom 3 in the next column. And the nice thing is you've already summed those 3, right? You did it for the first column. So if you save that as a variable, then you can reuse it, and that speeds up your computation. So that means that you can take your tree summation algorithm from n squared in image size to n log n, which is really nice. And that kind of computational speed is the reason we use tree summation instead of Hough transforms when we're just searching like a giant block of data in our breakthrough list n searches with TurboSETI. There's a lot of stuff that shows up in my paper that I don't know if I want to go into too much detail about, but one thing that I did think about was, well, there is a maximum drift rate that you can search up to, because in this right image here, if the signal's drifting any faster than one frequency channel across the whole, one time bin across every frequency channel, so it just zips through your detector because it's drifting so fast, it doesn't really matter if it's going from, say, a slope where it's the top corner here to the bottom corner over there, or something that zips through your bandwidth so fast that it's almost horizontal. All of those will look the same because they pass through the same pixels. So that does provide an upper limit, and I was like, oh, well, maybe that's what I can use. Spoiler alert, it's stupidly high and not very reasonable to choose. So that was a thought I had. It didn't quite work out the way I wanted. That would be a nice way to do it, but because our receiver is so large, at least at Green Bank, we're covering 4 gigahertz, maybe up to 8 gigahertz of bandwidth. Something that was drifting so fast that it went through the whole receiver in, say, 20 seconds would be accelerations that are kind of ridiculous and not really physical. I'm probably going to skip this part. The very short summary is if you have a signal that's drifting fast enough to go through multiple frequency bins in the same time bin, kind of shown in this middle image, then you have to collapse your frequency resolution to kind of integrate those pixels together if you want to be able to do these same algorithms on that array without losing power. So past that point, your search speeds up because you've cut your array in half, and you can kind of iteratively do this. So if you really care about computation time, this can be a useful little trick. I have animations. There we go. So to summarize all of that, why do we want to choose a maximum drift rate? Because for both of these algorithms, they're order n in drift rate. So if we want to search twice as many, it'll take twice as long. So we've better have a pretty good reason for wanting to search 2 times as many drift rates if it's going to double our search time. Cool. So that's kind of the computer sciencey side of my talk. Now I'm going to get to the astrophysics side. So we now know that we expect to see drift rates coming from any signal that's being transmitted from an accelerating system. And we don't want to search all of the drift rates that we can because that takes a long time. We want to set some reasonable limit. So what reasonable limits can we set from observation, and what reasonable limits can we set from theory? So this is where we get into some fun exoplanet stuff, because now that we know of thousands of exoplanets and we've characterized, in many cases, their radii, and in almost all cases, their semi-major axes, we can figure out what contributions we expect to the acceleration that some transmitter is undergoing when we're trying to receive a signal from that system. That was a bit of a complicated sentence, but hopefully this diagram helps explain it a little in a bit of a simpler way. So if we have a receiver that's sitting on Earth, Earth is rotating, right? So there's already some relative acceleration, even if your transmitter was perfectly stationary. Because Earth is rotating, you're going to get a little bit of a contribution from Earth's acceleration from rotation. Same thing, Earth is going around the sun, so we're moving relative to the thing we're trying to observe. That gives you a contribution of acceleration. So there are two that just come from our own solar system. Then we'll assume for now that we've placed a transmitter from an ETI on a planet. That planet is rotating, so that gives us a contribution of acceleration. And that planet's also going around its host star, and that gives another contribution. So once you add all of those together, sometimes they'll be in the same direction, sometimes they'll be in different directions, you'll get some total relative acceleration, and that's going to contribute to your drift rate. So actually, I'm going to go back a slide real quick. This is a great time to mention that these accelerations aren't always nice and linear. They're going to change over time. For example, if you think about the sine curve I showed of the radial velocity, if you take the time derivative, you get a cosine, right? It's not linear. It'll depend on where it is in the orbit. But if you only observe for a short time compared to the whole, say, orbital period of the planet, then you can approximate it as linear. If you zoom in on that sine wave enough, it'll look like a line. So I'll come back to this later, but I just wanted to kind of be clear that if you look for long enough, these things are not linear. You'll see weird kind of sine wavy looking curves going through your data. But because we're only observing for a short amount of time compared to orbital periods or rotational periods, we're okay and we can approximate it as linear. So I basically took that diagram and plopped it into a time derivative of Doppler shift equation here. And what it comes down to is you have four terms, two from the Earth and two from your exoplanetary system where your transmitter is. So these ones in the yellow box are from Earth's rotation and orbital motion. And those ones we know. We know, like, our telescope is at this latitude, we're pointing in this direction, and Earth is rotating this way. So there's this relative acceleration. I don't want to personally do that calculation, but AstroPi can do it for me. So those terms we don't have to worry about. The terms in blue and green here are the contribution to the drift rate that you get from the host body just rotating, and the contribution that you get from the host body orbiting around something else. So those two are completely unknown when we just point our telescope at something. And those are the ones that we want to try and constrain based on what we know about exoplanets. And finally, I added this pink term here for fun. That's any other radial acceleration that you might get. So say your transmitter's on a spaceship that's accelerating towards Earth. That's another contribution that's not included in the other terms. Here, we're just gonna set it to 0 for now, but I did want to put it in there because if for some reason you have something accelerating under its own power, it doesn't fit within this nice sitting on a planet framework. So now, what I did was I went and looked at all of the possible bodies in our solar system that we knew rotation rates for. And I said, if I stuck a transmitter on this and observed it from Earth, what's the maximum drift rate I would expect? So what's the maximum slope in that waterfall plot that we would see if we looked at it at just the right time, or the wrong time, as the case may be. So I went through the asteroid-like curve database, trying to find asteroids and small bodies with known rotation rates. And there's one outer main belt asteroid whose rotation period and size kind of maximize the drift rate you would expect. So it rotates every like 5 minutes, very fast rotator, It's about 3 kilometers in size. It's in the outer part of the main asteroid belt. And if you stuck a radio transmitter on this thing and observed it at just the wrong time, you would see the signal drifting at 4.2 nanohertz. Now remember, I put in the corner here, about 50 years ago at this point, Project Cyclops said you should search up to 1 nanohertz, but don't bother searching at higher than that. And already, based on that guideline, this asteroid, if it had a transmitter on it, you might not pick up with your algorithm because you would have set your maximum too low. So it's already 4 times the guideline. And as a spoiler, it's only going to get worse. So we have a lot of knowledge about how things rotate in our own solar system. Turns out it's pretty tricky to measure that for exoplanetary systems. We have some measured rotation rates for really, really big exoplanets, but none for terrestrial exoplanets so far. So just as a case study, the planet Beta Pic b, which is fun for a lot of reasons, has a mass of 8.5 Jupiter masses. So this huge gas giant. It's one of the few planets that we're able to get a rotation rate for that's not in our solar system. And if you kind of plug in all the numbers, you end up with a drift rate of 19.4 nanohertz. And I will completely admit here, this is a giant gas giant, a large gas giant. So you wouldn't expect to be able to build a transmitter on its surface, but you could build a transmitter, say, on a moon in orbit around it. And so this just gives us some idea of what drift rates we would expect from exoplanetary systems, even if you can't actually build a transmitter on the surface of a gas giant. So then I started thinking, well, what's the fastest a planet can spin? Because that would be a great upper limit. We can say no planet can be spinning faster than this, so that could be our upper limit on rotation. And the physics behind this gets very complicated once you start taking into account actual materials, but you can do kind of a rough approximation by looking at the breakup speed. So this is the rate at which the centrifugal force on the surface of your planet is equal to the gravitational force at the equator. So if it spun any faster, material would start flying off at the equator. So to give you an idea, this is like an 80-minute-ish period for the Earth. And I played around with some numbers and said, okay, what is the, like, if I play with planet parameters, what's the fastest I can get something spinning, and the largest and the densest to get the highest drift rate. And once I kind of optimized for that, I found that you can get up to 309 nanohertz for a 6 Earth mass super Earth, if you kind of had the perfect storm. 300 times the original guideline. Of course, this is like 6 Earth masses of iron rotating at a breakup speed. But the idea of the project is to try and just set like hard upper limits. So with this breakup period, we can say, well, from rotation, we don't expect any terrestrial planet to be able to surpass about 309 nanohertz. So that's an upper limit, but I'm not going to stop there. So that's rotation, but what about orbital motion? So let's say the planet isn't rotating crazy fast. It's just maybe a normal 24-hour day like we have on Earth. But can the orbital motion from it going around its host star have a large contribution to the drift rate? So because we have to think about radial accelerations, we can play around with eccentricities of orbits. And say, well, if we looked at it just at the wrong time, when it was at its highest point of acceleration around its host star, what would the drift rate be? So then I went into the Minor Planet Center Orbit and Observation Database for things in our solar system. And in our solar system, there's this near-Earth asteroid, 2006 HY51, with a semi-major axis of 2.59 AU, but a crazy high eccentricity, so 0.97. And when it's at periaps, so when it's closest to the sun, you would be able to get a drift rate of about 3 nanohertz from a transmitter on its surface. So compared to the giant ball of metal spinning as fast as it can, 3 nanohertz isn't a ton, but again, note that it's higher than what the previous guideline was. So even things in our own solar system are accelerating fast enough relative to Earth that you need a pretty high drift rate to account for them. So then again, moving from our solar system to exoplanets, there's an exoplanet HD 80606b, which is a lot of people's favorite exoplanet because of its very high eccentricity. So same idea. What drift rate would you get when that planet is at periops? And plug in all the numbers again to that kind of equation I showed in the beginning, you get 22 nanohertz. And finally, one more case study. What about all of these really compact systems that we've been discovering around red dwarfs? So one M dwarf system is Kepler 78, which has a planet Kepler 78b with kind of the parameters I've shown here. And it's orbiting with an 8.5 hour period. So just zooming around its host star, very, very close at 0.09 AU. So super, super close to its host star. And just from orbital motion, if we observed it at just the wrong time, you would get a drift rate from a transmitter on it of 191 nanohertz. Huge, huge numbers. And these are planets that we know exist. These are characteristics of planets that we have found, often via Kepler or other transit missions. So again, let's move from observed to theoretical and see if we can push this even more. So the largest accelerations that you can get from an orbiting exoplanet system are when you're as close as possible to your host star. So that closest possible orbit is basically when your object would be torn apart, is kind of your Roche limit, so that's one way to choose it. In this case, I think I just set the closest possible orbit to be the radius of the inside body. So even if you had a satellite in orbit, we're gonna say that it no longer exists once it's inside the host star. So set that as my limits, and there's a table here of the different drift rates you would expect. And for tiny M dwarfs, this drift rate can get extremely high because you can get very, very close to the star because of its small radius. So just from orbital motion, like these are the numbers that we would expect as these kind of theoretical maxima. Okay, so then I don't know if any of you have thought of this, but my next thought was like, how can I push this even further? What way can I maximize these accelerations even more? And if you want very large accelerations, you need very strong gravitational fields, and that means compact objects. So at this point, it starts getting kind of ridiculous because to properly characterize what sorts of drift rates and accelerations you would expect, you have to start doing some really nasty general relativity stuff, and the equation I put before stops working. But as some kind of order of magnitude numbers, if you are in orbit as close as possible to a neutron star, you can get drift rates of up to 10 to the 13 nanohertz, which if you take that from nanohertz to normal hertz, you're drifting kind of straight through breakthrough listens bandwidth in, say, a normal 20-second integration. So if you have something that's orbiting there are a bunch of other things you have to take into account, because now you can't approximate it as linear, there's general relativity, it's a mess, but I just kind of wanted to see how large I could get these numbers. So the main conclusion of this part of the paper is that if you're interested in looking for transmitters around black holes or neutron stars, you have to do more math, and I'm not going to do it here. So that's kind of where all the analysis went into, looking into those databases, finding the most extreme objects, maximizing for drift rate, and then doing these theoretical calculations of how high the drift rate could get. So how does that compare with what we have been doing in the field? So this was my big, beautiful plot that I was very proud of. That is kind of the main result of the paper. And they say never to put tables in talks, so please don't try reading every line of this. But I do want to highlight a couple of rows. So basically, I've taken all of those calculations I did in the previous section and ordered them by drift rate in this table. And I've highlighted a couple of important values. So in yellow is the Project Cyclops guideline. That's that 1 nanohertz drift rate. And if you decided to use that guideline for your algorithm and you said search up to this slope, you would catch any object above it, above the line in the table, but you might not catch anything below the line. So if there was a transmitter on Oumuamua, you would catch it. If there was a transmitter on Mercury or on Earth and you were observing the Earth from somewhere else, you would catch it. But if you put a transmitter on Io, your algorithm might not catch that signal because it's drifting faster than the maximum drift rate that you chose. So the main thing that you should notice is how many rows of the table are below that guideline, and even including Io and Jupiter, which are in our own solar system. So breakthrough listen here, I highlighted at 7.2. We really use a range of drift rates depending on the search. So it could go down to 20 or so, or up to, I think, 5-ish, 10-ish. So it's kind of this range, which is better than the Project Cyclops guideline and better than most searches that have been done in the past. But there are still a lot of known exoplanet systems that if we observed them and they had a transmitter in them, we might not catch it because their drift rate could be higher than the maximum we're choosing. So based on that, in this paper, we recommend 200 nanohertz to be the input maximum drift rate that you're using. And that would catch every observed system that we have seen. If it had a transmitter in it, we would be able to observe it with those algorithms that I was talking about earlier in the talk. There are a lot of rows below this, but these are all kind of those theoretical upper limits where it's like, okay, we make the planet entirely out of iron. We spin it as fast as possible. We put it at the surface of its host star. Kind of these more constructions that are more out there. So considering all of the different numbers that we got, 200 is a good upper limit for drift rates in SETI searches. And just to kind of illustrate this and hammer in that point that the linearity only works so far, this is a plot that's sort of like a simplified waterfall plot. So frequency displacement, how much it has drifted on the bottom, and observation time on the top. So the observation starts at 0 and goes for 5 minutes, which is kind of typical for breakthrough listen. And the gray line here is the breakthrough listen maximum slope that we use. So that one I think I put at, I want to say it's a 10 hertz per second at L band. I should have put that number on here. But it would catch any slope that is less than that in this plot. So all of these dotted and dashed lines down here are objects that the breakthrough listen maximum drift rate would already catch. But I'm sure you've noticed this fun little sine curve here, which is 2008 DP4. So that's one of the near-Earth asteroids I talked about. And over a 5-minute observation, it's rotating so quickly that if there was a transmitter on its surface, you wouldn't see a linear signal. You can't approximate it as linear anymore because it's rotating multiple times through your observation. So then you have to start thinking about how you would write a new algorithm to be able to pick up on these sine curves. And that's something that people have worked on a little bit, but it only matters for things with really short periods. And for the most part, we've swept that under the rug for now. But I did want to show this figure to kind of illustrate that it is something that you have to think about if you want to observe something that you expect to have a very short period. All right, so that's what I had. I'm just gonna kind of summarize in a couple of takeaways. First of all, the thing that I learned doing this project was that the drift rates that can be produced by known astrophysical systems are way larger than the maximum drift rates that we had been choosing in SETI searches in the past. And that's partially because a lot of people were using that Project Cyclops guideline that was sort of an order of magnitude and not meant to be used again and again, but it just became the number that people went to. And partially because of computational constraints. When that number was derived, you couldn't search up to 200 nanohertz. That would be ridiculous. Now we actually have the ability to do that. So, like I said, main takeaway, if you remember one number, 200 nanohertz, which is hertz per second at a gigahertz, which is large enough to encompass every system that we have observed, both within our solar system and outside of it. You can get larger than that in theory, but we haven't observed anything that would surpass that. From that algorithm section, drift rates scale linearly with the common algorithms that we use. So if we want to go to 200 nanohertz and we were searching at 1, it's going to take 200 times longer. And that's asking a lot, but some of these algorithms can be parallelized, and you can think of the 200 as like an aspirational goal. So far, Breakthrough Listen hasn't done any searches up to that 200, but I am currently in the process of trying one. The analysis is ongoing there, so it's something that we're striving towards. And finally, the more you read into the literature in any subject, the more you'll realize that scientists often invent the wheel multiple times, but it's in different disciplines, so they don't know that it's been invented before. So what I learned from this project was that the methods that we're using in SETI searches, the methods that are used in image processing, and methods that were developed for pulsar research are very synergistic, and there are many techniques that we could borrow from those fields or even teach to those fields that we've developed for SETI that would really help speed technology and development and code development especially. So always keep an eye outside your own field.